far as solution compositions go, we have the percent, ppm, part per billion, etc. We also have molarity. Molarity is much more convenient for stoichiometry. So molarity, the definition is moles of solute per liter of solution. We looked at molarity already during our titration calculations. But to calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide in water and diluting into 1.00 times 10 squared milliliters. And so we need, for the molarity of sodium hydroxide, we need the moles of sodium hydroxide. So we'll just go from grams of sodium hydroxide to moles of sodium hydroxide using the molar mass. And over the volume of sodium hydroxide solution. The volume of the sodium hydroxide solution here is 100 milliliters, which would be 0.100 liters. So the first step is to figure out how many moles, 0.38 moles of sodium hydroxide, pure sodium hydroxide. And then how many liters of sodium hydroxide solution. We have 100 milliliters of sodium hydroxide solution, which gives us 0.100 liters. Then take the moles divided by the liters. Here. And that gives us the molarity. It would be 3.8 molar sodium hydroxide. In other words, 3.8 moles of sodium hydroxide, pure sodium hydroxide per liter of sodium hydroxide solution. Molality is another option that we can use. Molality is somewhat similar. It's moles of solute, like molarity, except the difference is rather than liters of solution, this is kilograms of solvent. So it's unusual. It's not kilograms of solution, but kilograms of just the solvent. The advantage of this is temperature independent. That is, molarity changes with temperature. Volumes expand and contract with temperature, but kilograms don't expand and contract with temperature. Kilograms stay fixed. This does moles. So how many grams of potassium chloride must be dissolved in 250 grams of water to make 0.400 mol solution? So 0.400 mol solution is 0.400 moles of potassium chloride per kilogram of water. So 0.400 moles of potassium chloride per kilogram of water. Water is the solvent. And so if I have 250 grams of water, then what I'll do is this. I'll go from 250 grams of water, pure water, to kilograms of water. From kilograms of water, I can use this to go from kilograms of water to moles of KCl. And then from moles of KCl, we'll just go to grams of KCl. So it's just a dimensional analysis. So grams of water to kilograms of water to moles, using the molality, and then moles to grams.
If you have 0.4 moles solution, does that mean that it's 40% by mass, that thing that this?
No, if this were, let's say solution, possibly. The moles, though, weigh's different. It's not necessarily 40% by mass. If it's 0.4 moles like this, mole, maybe I'm missing something. If it's like let's say if it's 0.4 out of 1, 0.4, that is a mole fraction. Let's say you have 0.4 moles of KCl out of 1 mole total. So it's a mixture, there's some other stuff in there. Then this would be 40%. But this is kind of weird because it's 0.4 moles of KCl over 1 kilogram or 1,000 grams. And so the units don't quite work out. It could still be a percentage. This would be 0.4%, but what would you call it? Parts? In terms of moles, it would be a mole kilogram percent. We can have composite percentages, but this is in terms of solvent. A composite percentage would be something like this, which is very common. percent. This is called an MB percent, NaCl. And so what this means is this. It means that there's 0.9 grams of sodium chloride, pure sodium chloride per, not 100 grams of solution, but this will be 0.9 grams of pure sodium chloride per 100 milliliters of solution. And so 0.9 grams of sodium chloride over 100 milliliters of solution gives us a 0.9% MV sodium chloride. You know what they call that? 0.9% MV? You can buy it. .9%. We call it saline solution. And it's normal saline solution. And we use this intravenous solution. 0.9% saline solution. This concentration is kind of interesting. Because this concentration has the same concentration as your blood, and so the cell, the intracellular fluid, your blood.
Why isn't it a decimal?
Oh, this is a European manufacturer. Europeans, they don't use decimal; they use
Okay, that's right.
commas.
That's the stuff put to your.
Right. This is the stuff that they drip into your saline drip.
You
This
can
one.
buy it over the counter.
What's that?
You can buy it over the counter.
You can buy it. I think they sell this, like at the pharmacies. They sell this stuff. I saw it on the shelf. Saline solution. People use it for different things. Let's find a U.S. manufacturer. Where did I see it? This is injectable here. I think I saw it in something like this. Growcells.com. I think this is used for growing cell cultures. 0.9% saline. They call it isotonic. This is isotonic with blood. And this is a wide variety of molecular and cellular biology applications. This sterile saline. And so this is where you get a weird percentage unit. That has a different, most of the percentages that we deal with would be grams over grams. 0.9 grams over 100 grams. This one's just odd.
Is there a certain percentage of NaCl that you can dissolve in water that the water will be like completely saturated and it won't dissolve anymore?
Yes, there is. There is. But the percentage would be 36. It'd be 36% M over V. So we could see what it is here. This is a bit unusual for the units. It's a bit unusual for the units because this is 360 grams per liter. Usually the units they do are grams per 100 milliliters. And so if we do it in grams per 100 milliliters, then it's 36 grams per 100 milliliters, 0.1 liters. And so as far as percentage goes, do you see this is going to be a composite unit too? On the top we have mass, on the bottom we have volume. And so what we have to say is this is going to be a 36% M over V. And so 36% is the highest you can go. And so that, the saline solution is only 0.9% M over V. This would be 36 is the max. You wouldn't want to do 36% because you know what, if you put 36% intravenously, you know what that's going to do to your cells?
It dehydrates them. There's a word for it. It's not lysine. That's when they burst. It's the other one.
Yeah, it's the other one.
Not isotonic.
Yeah, this would be hypertonic.
Thank you, hypertonic.
It would be hypertonic. And then if you see what that does to your cells, then we can see.
It's like drinking salt water.
Right, it's pickling. This is what happens. If you put that kind of, the reason it's 0.9% is you want to maintain your red blood cells like this. This is isotonic. If you put anything higher than 0.9%, then you're going to pickle your cells. Pickling your cells is called crenation. And then if you put something less than 0.9%, then your cells start to fill up with water, and then they can burst. It would be lysis. So 0.9% is important. This is isotonic. They call it shriveled here. Lysed, shriveled. That makes sense. Swollen, shrunk, normal. Well, anyway. And it's just what happens. Okay, that's molality. The molality, you know, we wouldn't really do it with molality because it's only the solvent. We're missing something. It's per kilogram of solvent, and that's not the total mass. You know? So with molality, it doesn't quite work out. Kilogram of solvent, we're missing the solute, and so this is just part of the total mass. You can still make a percentage. You can make a percentage out of anything. But it wouldn't be very useful in that case. This one's not so useful unless you're doing lots of titrations. This is called normality. And so anything that deals with normality, we're going to skip it. So this is normality, skip it. Normality, skip. 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 And so these are the common units for expressing the composition of solutions: percentage, molarity, molality. We use molarity the most because of the stoichiometry. Normality, not. Well, one of the things you do, you know, when you buy, let's say you buy detergents or soaps or whatever, usually if you buy like dishwashing soap, you want to buy the concentrated stuff, right? You don't want to buy the dilute stuff. Then we'll dilute it, or cleaning agents. So you buy it concentrated. The same thing with chemicals. We buy chemicals that are concentrated, and then we dilute it to whatever concentration we want. And it's just more economical that way. And so what we have to do in lab a lot is solution dilution, because when we buy HCl, let's say we buy concentrated HCl, then we want to dilute it. We want to dilute it to a whole bunch of molarities, like 6 molar, 1 molar, 0.1 molar, a whole bunch of different ones. And so that's going to require solution dilution. Solution dilution is an important calculation in lab. And so the solution dilution equation is this. It's M1V1 is equal to M2V2. Or your book has it like this. The concentrated MCVC is equal to MD dilute VD dilute. I'm just going to do it this way, M1 V1. Therefore, if we want to figure out the molarity 2, this is the dilute molarity, then what we do is we take the volume 1 divided by the volume 2 times the molarity 1. This first factor here, this is called the dilution factor. Dilution factor is the initial volume divided by the final volume. That's the dilution factor. And so we could look at the dilution factor here, just eyeball it. If we look at it, okay, here's the initial volume, we'll call it 1. What's the final volume? You say double the initial volume? It's like more than double, doesn't it? It looks like the final volume's triple, doesn't it?
Yeah.
And so this is what we call a 1 to 3 dilution. Initial volume 1, final volume 3. So it's a 1 in 3 dilution. So 1 to 3 dilution means that we'll have 1/3 the original concentration. And so this will be 1/3 the original concentration. Here. That's the dilution factor. This is here's the original concentrated one, 100 milliliters. And then we do all this work and dilute it. Here's the final. So what we want is the final and we want the initial. The initial is 100 milliliters. The final volume, you know what it is? 1,000 milliliters. These are volumetric flasks. Volumetric flasks are really expensive, but they can be used to precisely measure the volume. So this is actually 100.00. This is 1,000.00. So 100 to 1,000. So our initial volume is 100. Our final volume is 1,000. So I just do it like this. Initial volume 100, final volume 1,000. Let's knock off 2 zeros. It's a 1 to 10 dilution. What was my original concentration? Original concentration was 0.100 molar. And so if I do a 1 to 10 dilution of 0.100 molar, what's my final concentration going to be? It'll be 1/10 that. 1/10 this is 0.0100 molar. And so my final concentration will be 0.0100 molar. This is it. And this is how you do it. How you do it in practice is, okay, we measure out a quantity here, and then we dilute it. When we dilute it, we'll dump it into this flask here. And we don't get all of it, so we gotta rinse it in here. Once we rinse it in there, then we'll just fill this up until we hit the 1,000 milliliter mark. That is, we don't do it like this. We don't pour in 1 part of this and then 9 parts of water. You know, this is too much work for one, and sometimes the volumes don't mix properly. What's easier is just to fill it to 1,000 with water. So that'll give it to us. How many milliliters of commercial hydrochloric acid, which is 11.6 molar, should you use to prepare 5.50 liters of 0.500 molar hydrochloric acid? And so you buy the concentrated stuff and then you dilute it to what you need. And so in this case, we need half a molar, 0.500 molar. And so the initial molarity 1 is the concentrated stuff, 11.6 molar. And then volume 1 is, I don't know how much of the concentrated stuff we need. I know I want to form as molarity 2.500 molar, and I need how much of it? I need 5.50 liters worth of it. And so I'm going to solve for V1. If I solve the solution dilution equation for V1, V1 is equal to M2 over M1 times V2. So I have the factor there. So the molarity of the dilute is 0.500 divided by the molarity of the concentrated, 11.6. So this is the fraction, the molarity fraction, and the volume is 5.50 liters. So what fraction of this volume is going to be the concentrated stuff? Figure that out here. .237 milliliters. So it comes out to 0.237 237 liters, which is 237 milliliters. Remove the decimal number. And so what we'll do is we'll take 237 milliliters of concentrated stuff and add enough water so that the total volume comes out to 5.5 liters. And that would give us the proper dilution. Okay, this is solution dilution, that's a lab technique. Now let's go to the stoichiometry. Stoichiometry, the easiest unit to use is molarity. So we look at the total stoichiometry map. Here we have the volume of the solution. If we have the volume of the solution, we can go straight to moles by knowing the molarity. Likewise, if we know the moles, we can go straight to the volume by knowing the molarity. Calculate the volume in milliliters of 0.842 molar sodium hydroxide required to precipitate as copper 2 hydroxide. All of the copper ions at 30.0 milliliters, 0.635 molar copper 2 sulfate. Well, this is a stoichiometry problem. So for a stoichiometry problem, we need the balanced chemical equation first. And so what is the balanced chemical equation for this reaction?